Hello, everyone, and welcome to this week's lesson. We are going to start to talk about global climate change. And in this unit, this week we're going to talk about the chemistry of Earth's atmosphere. And the learning goals for this week are to develop a model to explain what happens when the sun's energy is absorbed by the Earth's surface and then converted to infrared radiation. Describe how a greenhouse gas differs from other atmospheric gases such as nitrogen and oxygen. Describe the three ways molecules oscillate as they absorb energy and identify the most common greenhouse gas. Okay, this is lesson 1, the greenhouse effect. The greenhouse effect is part of Earth's surface energy budget, which we learned about in previous lessons. It begins with incoming radiation from the sun, mostly as visible light. So in the greenhouse effect, we are going to learn about what it is. Climate change is one of the most interesting topics of geoscience because it combines the sun's fluctuations, planetary orbits, atmospheric chemistry, radiation physics, ocean circulation changes, and biomass and land feedbacks. So there's a lot going into understanding greenhouse effects. It's not just chemistry. There's biology and physics involved, as well as geology. It's also a highly relevant topic because of its impact on human society, from the past, the present, and the future. Currently, the biggest changes to climate involve increasing greenhouse gas concentrations. So to understand climate change, we first need to understand the greenhouse effect. So here we have a diagram of Earth's energy budget. The greenhouse effect is part of Earth's surface energy budget, and it begins with incoming radiation from the sun, mostly as visible light. So we can see that in this picture. So we can see this incoming solar radiation, and we can see that there are 77.1 watts per meter squared are absorbed by the atmosphere. And then we can see, so that's incoming solar radiation, there's 340.4 watts per meter squared, and 77 watts per meter squared is reflected back by the clouds in the atmosphere. And then by the surface, 22.9 is reflected by the surface. 163.3 watts is absorbed by the surface. It goes into the earth. So this is about stuff that's absorbed by the sun. And then we have stuff that is radiated back out. So 398.2 watts per meter squared is emitted by the surface. So that is going to be re-radiated out as infrared, as heat. Some of that is absorbed into the atmosphere, 358.2. Some of what is absorbed by the atmosphere later gets emitted back into space by the atmosphere. Some is emitted by the clouds. And so all of this goes into the greenhouse effect. So the Earth's energy budget describes the various kinds and amounts of energy that enter and leave the Earth's system. It includes both radiative components, such as light and heat, that can be measured by CERS, C-E-R-E-S, and other components like conduction, convection, and evaporation, which also transport heat from Earth's surface. On average, and over the long term, there is a balance at the top of the atmosphere. The amount of energy coming in from the sun is the same as the amount going out from the reflections of sunlight and from the emission of infrared radiation. Now, everything is in balance in a normal system, but sometimes a system isn't normal and the balance can be thrown off. And that's from greenhouse gases. So a greenhouse gas are gases that are effective at absorbing wavelengths that correspond to infrared radiation, the kind of energy the Earth's surface emits. So the Earth's surface emits infrared radiation to go back into space. Now, some of it doesn't go back into space. Some gases absorb that certain wavelength of infrared light energy. And the greenhouse gases keep Earth's surface about 35 degrees Celsius warmer than it would be without those gases. So you should know that all gases absorb electromagnetic radiation. Now, when we learned about what is light, we learned that certain atoms, certain elements, will absorb energy at very specific packets of energy at a very specific wavelength called a photon. And in order to produce or emit light or other kinds of electromagnetic radiation has to be at a very specific wavelength. So that's why different gases will emit or absorb specific wavelengths of radiation because they're made out of different elements. And certain elements will absorb different wavelengths of light better than others. So most of Earth's atmosphere is nitrogen and oxygen. 78-ish% of the atmosphere is made up of nitrogen gas. It's not all oxygen. Oxygen's like 12% or something. But most of it is nitrogen. And nitrogen and oxygen, they're not very good at absorbing that infrared radiation. So they are not greenhouse gases. Greenhouse gases exist in small amounts. Most of the atmosphere is not made up of them, but they absorb enough heat to keep the Earth's surface, like I said, about 35 degrees warmer than it regularly would be. So we're going to look at global warming potential, GWP. It's a measure of the heat trapping capacity of a greenhouse gas over a given period of time compared to that of a similar amount of CO2. So there's different kinds of greenhouse gases, and some of them are better at trapping and absorbing that heat energy than others. So an interesting thing is most of the greenhouse gases are increasing in the atmosphere due to human activities, except for fluorocarbons or CFCs, because they've largely been outlawed. In fact, just this year in January, CFCs were outlawed in new air conditioning devices. Freon, which was used in air conditioning, is no longer allowed in California because of those CFCs. CFCs used to be in different aerosols like hairspray, but they're no longer in them. Engineers and scientists have figured out new ways to make air conditioners and hairspray cans and spray paint cans. They don't emit any CFCs. So CFCs have actually gone down significantly since the 90s, which is great. So let's look at some main greenhouse gases. You guys are probably familiar with carbon dioxide and methane. But there's other different greenhouse gases, including some CFCs, that you might not know so much about, and you might not know where they come from. So nitrous oxide is another greenhouse gas. You might know of nitrous oxide or NOx if you're into like racing cars. It can make cars go faster. It's also used as a sedative in medical use. So if you've ever had like a tooth pulled or like a cavity, you might have gotten something called laughing gas, which is nitrous oxide. So, but it's also found in fertilizers and other industrial processes and combustion. We can also get nitrous oxide from those. Okay, so if we look at this, we can see, we can look at the chemical formula. We can look at their pre-industrial concentration. So before the Industrial Revolution, before we have a lot of industry and factories and things like that, how much was in the atmosphere? And then this is a little bit old of a graphic, but it shows us the concentration 1994. And like I said, for the CFCs, those have actually gone down quite a bit since 94, but we'll just go with it. Okay, so if you look at carbon dioxide, the pre-industrial concentration was 278,000 ppBV, and ppBV is 1 part per billion by volume. Now we're up to 358,000, and the amount of time it spends in the atmosphere is variable. We looked at the carbon cycle, and it's in and out in the atmosphere all the time. I think the average amount of that carbon is spent was about 15 days, if I remember from last week's lesson. And where do we get that carbon dioxide in the atmosphere? We get it from burning fossil fuels, from land use, and from cement production. The global warming potential of carbon dioxide is 1, because it's the standard. The global warming potential is all based around carbon dioxide. Okay, methane. Where do we get methane from? Well, we get it from your farts, but you can also get it from fossil fuels, rice paddies, waste dumps, and livestock, because cows fart a lot. So before the pre-industrial revolution, we had about 700 parts per billion by volume, and now we have about 1,721. So that's, more than double. It's their lifetime years. It's in there for about 12-ish years, give or take a few years. And the global warming potential is 21. So that's a big difference. Nitrous oxide. There used to be about 275 parts per billion by volume, and now there's 311. So it's been up a little bit. And it stays in the atmosphere for about 120 years. And the global warming potential is 310. So that means it's really, really good at absorbing the infrared light or electromagnetic energy at specific wavelengths. So now we can look at some CFC 12. And there used to be none, because this is something that was pretty much invented, this chemical. So it's a man-made chemical. It's not a natural chemical. And now we have about 503 or so, 504-ish, just 503 parts per billion. And it spends 102 years in the atmosphere. Liquid coolants, foams, different kinds of industrial things that people made in mostly like the 1950s. There was this huge slogan in the 1950s, better living through chemistry. And they made a lot of different kinds of plastics and foams and lots of new chemicals, mostly by the DuPont company. A lot of it came out of the military for different things. And it was awesome and cool and cheap until we learned, oh, shoot, it's messing up our atmosphere. And look at that GWP on that guy. 6,200 to 7,100. That's off the charts. That's a lot. That's why we outlawed them in the 90s and, really are totally getting rid of them today because they were bad. So let's look at a CFC 22 or HCFC. And so once again, this was not around. And now there's about 105-ish in the atmosphere. And it stays about, let me see, about 12 years. And it's found in liquid coolants, so like air conditioners. It's Freon, and that's 1300 to 1400. Now I actually have some updated concentrations for 2019. I don't have them on this graphic, but I did look them up for you. So in 2019, the concentration of carbon dioxide was 415, that's parts per million. So it's not giving me the parts per billion. So right here, it's, so that's going to be a little bit difficult. My other ones are in parts per billion for you. So for methane, we were at 1,721 in 1994, and now we're at 1,866. So it's gone up some more. For nitrous oxide, we were at 311, now we're at 332, so it's gone up. For CFC 12, we were at 503, and now we're at 504. So it went up a little bit, but it should be going down now. And for our CFC 22, it's also gone up a little bit. It's at 233, but we're not putting more in, so it should go down after a while. Okay, so that is it for lesson 1. We learned about greenhouse gases. So stay tuned or go right ahead and go on to lesson 2. Thank you.